Okay, so talking now a little bit about molecular compounds. Molecular compounds are also known as covalent compounds, result when electrons are being shared between atoms. And this is going to be compounds that only contain nonmetals. All right? So, what is the following, or what is the resulting compound that will form when we combine potassium and oxygen ions?
Okay, so to do this, I need to know what the potassium ions are, right?
Yep, we need to identify what potassium ions look like, right?
And we have to find out what oxide ions look like.
Very good. Potassium ions and oxide ions. Okay. We can use the periodic table to identify what kind of ions they'll form, right?
Yeah, potassium, where is it?
It's number 19.
Element 19, okay, it's going to be a positive one?
That's right. It's going to be a positive one because of its location. Good. How about the oxygen?
That's -2, I remember that.
All right, 2 minus. All right, so if these two are going to come together, what is the resulting chemical formula?
K2O.
K2O. How did you do that so fast?
I just do the crisscross rule.
All right, so you put the charges on there down here as the subscripts.
That's right.
Okay, good. And now make sure we understand the basis of that. I need 2 of these potassium ions to combine with every one oxide that has a 2 minus. So here again, the number of these charges, there's 2 positives and 2 negatives, right? Okay, good. Here's one that you guys can work on by yourself now. You folks at home, take these 2 ions, combine them together, and see if you can get the right compound. All right. Push pause if you haven't had a chance to do that yet. Okay, what do you think, Fred?
If it's sulfide ion, that's -2, right?
Good. The sulfide ion is a 2 minus ion, and the iron is a what?
It says +3.
Okay, iron is +3. Now, recognize that the iron is right here, right? It's a transition metal. Remember that block?
Yeah.
And transition metals can have multiple charge states. So in this problem, they had to tell us what the charge state was on the iron so that we could identify what the resulting compound would be. Okay? Good. And if we use the crisscross rule, we see that the chemical formula for iron 3 sulfide is going to be what? Fe2S3, is that right?
Yeah, that's right.
And let's make sure we understand what's going on there. We have 2 of these Fe's. How many sulfide ions?
3.
3 sulfide ions. 2 minuses on the sulfide, whoops. And then 3 pluses on the irons, correct?
Yeah, that's right.
Okay, very good. So 2 to 3, and that's because the 6, the number of electrons that transfer, has to match up. Okay, wonderful. Now let's talk about naming these compounds, all right? It's pretty straightforward. We talked about it a little bit already. Sodium chloride is a nice model for us because we take the name of the first ion, or first metal, sodium, and we take the chlorine and we change it to ide. So potassium bromide, calcium iodide, cesium fluoride. All right, good. Aluminum carbide, magnesium nitride, all straightforward. Good. Polyatomic ions, potassium, and then just the name of that ion, right? Potassium acetate. Now, you might not know the acetate ion, right? But how could you figure it out?
I need to bring up the periodic or the polyatomic ion table.
That's right. Getting our polyatomic ion table here, and then identifying the acetate. Now, the acetate has a couple of ways that it can be portrayed, chemical formulas. C2H3O2, I think, is the preferred, but you also will see C3COO minus sometimes. All right, so there's our acetate ion. Here, this one here is our bicarbonate ion. We can find it here. There it is down there, the bicarbonate ion, right? Okay, so we're just, notice there's no mono, di, tri, nothing of that. If I have 2 carbonates, it's just aluminum carbonate. I don't need to say in the name how many carbonates go with aluminum, because simply by saying aluminum carbonate, the person who's listening knows, okay, there's aluminum in there, and there's the carbonate ion, all right? And they know, based on the periodic table location of aluminum, that aluminum has to be a 3 plus, and so from that information, they know what the chemical formula for aluminum carbide is, all right? Now, if, however, I say something like, I have some iron carbonate, that's a different story. If somebody tells you, I bought you some iron carbonate, I went to Walmart and I got you some iron carbonate, what do you say, Fred?
Thank you.
Okay, you could say that, but how do you know they bought the right stuff? Maybe they bought the wrong iron carbonate, right? How can you determine that? All right? Well, what you need to know is, did they buy iron carbonate with an iron that has a +3 charge, or iron carbonate that has iron with a +2 charge? All right? So for example, iron carbonate, where I have a 2+ iron coming together with CO3 2-, that combination is going to be different than iron carbonate with the 3+ and the CO3 2-, right? This resulting compound is going to be iron carbonate, and this one is going to be Fe2CO3, 3. Right? Did I do that right?
Yeah, that's right.
Okay, so these are two different iron carbonates. Now iron, how did I know that iron could have multiple charge states? Because it's a transition metal. When I say multiple charge states, I mean it can have a +2 charge or a +3 charge. Okay? So iron is a transition metal, and therefore when somebody says, I bought you some iron carbonate, what you need to say is, well, what kind of iron carbonate is it? Iron 2 or iron 3? When they clarify and say, I bought you some iron 2 carbonate, okay, where that 2 tells us the charge on the iron in the carbonate. What do you think the name of this iron carbonate would be?
Iron 3 carbonate?
That's right, iron 3 carbonate. Because that iron 3 carbonate, or that 3 is telling me what?
The charge on the iron in the compound.
That's right, the charge on the iron in the compound. Okay? So, when we're dealing with a compound that contains a transition metal, or anything down in here, all of these can also have multiple charge states, then we need clarification using this system that we insert when we're writing, or say when we're speaking, the charge state of our cation, of our metal that is in the transition metal zone that can have multiple charge states. All right? So that is why we have these different numbers, Roman numerals, and why they have different names accordingly. So here's one for you to look at. The platinate ion forms a compound with rubidium as follows. All right, that's the chemical formula for rubidium platinate. What is the formula for iron 3 platinate?
Can you bring up the polyatomic ion chart?
Okay, what do you want that for?
Let's look at the polyatomic ion. I'm not seeing it.
That's right. It's not there, right? Like I mentioned, there are a lot of polyatomic ions out there, and not all of them are always going to be available to us.
Well, how can we know what the charge on the platinate ion is?
That's a good question. If you look at this compound here, rubidium platinate, apparently, how many rubidiums were necessary to compensate for the charge on the platinate ion?
Oh, 3?
That's right. I have 3 rubidiums. Okay? Now, do I know what the charge is on those rubidiums?
No.
Well, actually, I do.
How?
See, if I bring in our periodic table here and see rubidium, where is rubidium? There's rubidium. And we see that rubidium has to have what kind of a charge?
Oh, it's a +1 because it's a Representative element.
Very good. Representative element, so it has to have a +1 charge. So that tells me that if I have 3, that this platinate has to have what kind of a charge?
A -3?
That's right. There's only one of them, so it has to have a 3- charge. Now that I know that that is what the platinate ion looks like, then I can know what its combination is going to be with the iron 3, right? Iron 3, what does iron 3 ion look like?
Oh, does that 3 mean the +3?
That's right. That 3 means that there's 3 missing electrons on the iron atom, making the iron ion, the 3+ iron ion. And I can see how these are going to come together. It's just going to be a 1-to-1 ratio because the platinate ion has a -3 charge. So the resulting compound is going to be 1 iron for 1 platinate, FePtO4. You see how we did that?
Yeah, okay, I see how we did.
All right. And the name of the compound has to be iron 3 platinate. Is that because there's 3 platinates?
What do you mean?
Am I calling it iron 3 platinate because there's 3 platinates or because there's 3 irons?
I guess, is that right?
Is there 3 irons in this compound?
No, there's just one.
Is there 3 platinates?
No, just one.
So the 3 is telling us what?
Oh, it's telling us the charge on the iron.
That's right. It's telling us the charge on the iron. Sometimes people forget and think that this is telling us the number of one of these ions. But it's not. It's telling us the charge on the iron. Okay? All right. What metal would be a reasonable candidate to replace the X in this ionic compound? Why don't you and your roommate, or if you're all by yourself, take a second and take a look at this one. Push pause. Think about it deeply. See if you can use your brain to relate it. It's a joke you haven't seen before, so it's an opportunity to do some real learning. Okay. Push pause. Okay, did you do it? Did you take time to try to study and try to figure out which one it is? Which metal would reasonably candidate to replace the X here?
I'm not sure I know how to do this one.
All right. Well, XPO4 apparently is some ionic compound. There's 1 X for every 1 PO4. What is the PO4 called?
I looked it up. It's called the phosphate ion.
All right. So good. You might have looked it up. You might have remembered. The phosphate ion right here, polyatomic ion chart, right? The phosphate ion, let's double check there. PO4, what's the charge on it?
3-.
PO4 3-. So that is one of our ions. It's the PO4 3-. So what does that tell us about the charge that's on X?
Oh, I guess it has to be a +3.
That's right. X has to be a 3+ charge. So if X is a 3+, could it be magnesium?
I guess.
Well, let's look. Where's magnesium on our periodic table?
It's right there. It's number 12.
Could magnesium form a +3 charge in an ionic compound?
I guess.
If it formed a +3, it would lose how many electrons?
+3 means it loses 3 electrons.
That's right. Then it would have 11, 10, 9 electrons. And that's not a noble gas electron configuration. So magnesium is not going to lose 3 electrons in an ionic compound. It's only going to lose 2 electrons. So the answer can't be magnesium. Follow that?
Yeah, I get that. Okay. Same thing with sodium then, right?
Right, because sodium only wants to form what kind of an ion?
A +1. And lithium. And scandium wants to form a +1 as... No. Well, strontium. SR. S star strontium?
Yeah, strontium. What kind of an ion does strontium want to form?
A +2. So it can't be sodium, it can't be magnesium, it can't be lithium, and it can't be strontium. Does it have to be scandium? What kind of ion does scandium form?
Well, scandium is a polyatomic ion, or sorry, a transition metal ion, right? So it has a couple of options. What can it form?
I guess it can form a... Well, I don't know.
Can it form a +3?
I guess so.
Let's see. If it has 21 electrons and it forms a +3, will that be advantageous to it?
Well, I guess it's going to have a noble gas electron configuration of argon.
That's right. 21, 20, 19, 18 electrons if it loses 3 electrons. So a reasonable candidate to replace X in this would be our scandium ion. Okay? Does that make sense?
Yeah, I follow that.
All right. Very good. Good job, Fred.